So, good morning everybody. In previous class, we discussed about the limit of a sequence. So, if x equals xn be a given sequence, then limit x equals xn or limit xn equals x, that means for all epsilon is positive, there exists some k following n, there is a natural number k such that modulus of xn minus x strictly less than epsilon for all n greater than or equals k. This is the definition of limit of a sequence or convergence of a sequence. Sequence x equals xn converges to x, that means limit xn equals x. Then, what about limit by using this argument? We try to compute the limit of some sequence. What is limit 1 by n? How to prove this limit 1 by n equals 0? Means, to prove limit 1 by n equals 0, sequence xn, let sequence xn equals, let the sequence xn equals sequence 1 by n. Now to prove limit xn equals 0. How? For let epsilon is positive. Epsilon positive means surely 1 by epsilon is also positive. Then by Archimedean property, there exists some k following n such that 1 by epsilon strictly less than k. 1 by epsilon less than k means 1 by k strictly less than epsilon. Now, for all n greater than or equals k, consider modulus of 1 by n minus 0. Modulus of 1 by n minus 0 equals 1 by n. But what is for all n greater than or equals k? 1 by n less than or equals 1 by k. So it is 1 by n strictly less than 1 by k. But what is 1 by k? 1 by k less than epsilon. Thus, for all n greater than or equals k, finally we have for all n greater than or equals k, modulus of 1 by n minus 0 strictly less than epsilon. Since epsilon being arbitrary, by definition we know that limit 1 by n equals 0. So, if xn equals sequence 1 by n, then limit 1 by n equals 0. This is proved by using the definition of the limit of a sequence or convergence of a sequence. What about or to prove that limit 1 by 1 plus n square? Prove limit 1 by 1 plus n square equals 0. Prove limit 1 by 1 plus n square equals 0 by the same arguments. To consider for epsilon is positive, then clearly 1 by epsilon is positive, means epsilon is positive, 1 by epsilon is positive. Okay. Now, what is 1 by 1 plus n square? 1 by 1 plus n square, we have n. 1 by 1 plus n square means n less than 1 plus n square or n square plus 1 for all n following n. It is true for every n less than 1 plus n square for all n following n. Therefore, 1 by 1 plus n square strictly less than 1 by n for all n following n. Agree. Now let epsilon positive, 1 by epsilon is positive, then by Archimedean property, there exists k following n such that 1 by epsilon strictly less than k. So, but 1 by 1 plus n square strictly less than n, so you consider, we have to, in order to show that limit 1 by 1 plus n square is 0, consider modulus of 1 by 1 plus n square minus 0. That equals modulus of 1 by 1 plus n square, but 1 by 1 plus n square strictly less than 1 by n, since n is a natural number, it is always positive, then 1 by n. Now for all n greater than or equals k, what about 1 by n? 1 by n strictly less than 1 by k, but 1 by k strictly less than epsilon from here. So it is 1 by n less than 1 by k, it is strictly less than epsilon. So we have for all n greater than or equals k, 1 modulus of 1 by 1 plus n square minus 0 strictly less than epsilon. Since epsilon being arbitrary, we know that we have limit 1 by 1 plus n square equals 0. Agreed. Now, we consider sequence. Now we consider a sequence. Consider the sequence. Consider the sequence x equals 0, 2, 0, 2, 0, 2, etc. Consider the sequence. So, to prove the sequence does not converge to 0. The sequence does not converge to 0. How? Assume that the sequence converges to 0. Suppose the sequence converges to 0, that means for all epsilon positive, there exists some k following n such that modulus of xn minus 0 strictly less than epsilon. Agreed. For all n greater than or equals k. That is from definition. Choose epsilon is 1. Epsilon is a positive quantity. Choose epsilon is 1. So what do you get? Modulus of xn minus 0 strictly less than epsilon become modulus of xn minus 0 strictly less than 1 means modulus of xn strictly less than 1 for all n greater than or equals k. Agreed. But when n is even, in given sequence xi becomes 2 when I is in, or xn becomes 2 when n is in even position. x2 equals 2, x4 is 2, x6 is 2. So when n is even, comma xn equals 2. So that therefore modulus of xn strictly less than 1, that's a contradiction. This contradiction is due to our wrong assumption. Hence the sequence does not converge to 0. So sequence 0 to 0 to etc. 0 to etc. that does not converge to 0, proved by using contradiction hypo. Contradiction. Now prove that limit next that's the problem. Prove that limit 3n plus 2 by n plus 1. 3n plus 2 by n plus 1 equals 3. If you take limit n tends to infinity, then that's immediate. By how to prove this one? By using the definition of convergence or limit of a sequence. Limit 3n plus 2 by n plus 1 equals 3. So you consider modulus of 3n plus 2 by n plus 1 minus 3. That equals, by taking LCM, it is 3n plus 2 minus 3n minus 3. Okay, so it is, by taking LCM, it is 3n plus, that equals 3n plus 2 minus of 3n plus 1 means minus 3n minus 3 divided by n plus 1 modulus equals 3n minus 3n cancelling, modulus of minus 3 by n plus 1 modulus of minus 1 by n plus 1 equals 1 by n plus 1. Agree. So 1 by n plus 1, that is strictly less than 1 by n. 1 by n plus 1 strictly less than 1 by n for all n following n, for all natural numbers n. Okay, so as usual, let epsilon is positive, then there exists some k following by Archimedean property. Since epsilon is positive, 1 by epsilon is also positive. 1 by epsilon positive, then by Archimedean property, there exists some k following n such that 1 by epsilon strictly less than k. Agreed. Therefore, for all n greater than or equals k, modulus of 3n plus 2 by n plus 1 minus 3, that is strictly less than 1 by n. According to this argument, is strictly less than 1 by n. Less than 1 by n means for all n greater than or equals k, 1 by n strictly less than equals 1 by k. So it is less than 1 by k, 1 by k strictly less than epsilon. Since epsilon being arbitrary, we have limit of 3n plus 2 by n plus 1 equals 3. So you can solve these types of problems by using the definition of the convergence of a sequence or the limit of a sequence. Sequence xn converges to x means for all epsilon positive, there exists a k fallen in with the modulus of xn minus x degree less than epsilon. So all of these problems are solved by using this definition of the convergency and by using the Archimedean property. Now, consider another problem. If a greater than 0, then prove that limit 1 by 1 plus n a equals 0. For all a greater than 0, then limit 1 by 1 plus n a equals 0, where n is a natural number. How? This is proved by using a theorem that we already proved. That is, n is a natural number, a is positive, so surely 0 less than na. For any natural number n and a is positive, clearly 0 less than n. 0 less than na, so na less than 1 plus na. That means 1 by na means 1 by 1 plus na strictly less than 1 by na. 1 by 1 plus na strictly less than 1 by n. Now consider modulus of 1 by 1 plus na minus 0. 1 by 1 plus na minus 0 equals 1 by 1 plus na, but 1 by 1 plus na is strictly less than 1 by na. 1 by na can be written as 1 by a into 1 by a. Since a is positive, 1 by a should be positive. And we know that, we already proved that limit 1 by n equals 0. So we have a theorem. The theorem says that let x equals xn be a sequence of real numbers and x following r, and a and b a sequence of positive reals, such that limit a n equals 0, then there exists some epsilon positive with a mod xn minus x strictly less than epsilon for all n greater than or equals n. According to that argument, here a is positive, 1 by a is positive, and limit 1 by n equals 0. A is positive, 1 by a. Put for more convenience, put a c equals 1 by a, then c is positive, and limit 1 by n equals, or limit a n equals 0. Then according to that theorem, limit a n equals 0, then xn equals x means limit 1 by 1 plus na equals 0. By using that theorem, 1 by 1 plus na, there is 1 minus 0 is 1 by 1 plus na, strictly less than 1 by na according to this argument, that equals 1 by a into 1 by a. Put 1 by a equals some c, then since a is positive, c is positive, and the limit 1 by n equals 0, then according to the theorem, it is limit 1 by 1 plus na equals 0 itself. Okay. We prove the theorem. X equals xn be a sequence of real numbers. Sequence n be a sequence of positive real numbers. Instead of a n, here it is c. Okay. And the limit a n equals 0. Limit 1 by n equals 0. That is the sequence of positive real numbers. Then there exists, for all epsilon positive, there exists some m fallen n such that modulus of xn minus x strictly less than epsilon or less than or equals c into a n. According to that argument, limit 1 plus na, then limit xn equals x. Agreed. So the modulus of xn minus x less than or equals c into a. What is c? Here c equals 1 by a, means 1 by a into, what is sequence a? Sequence a n equals 1 by n. So it is modulus of 1 by 1 plus na less than or equals c into, instead of c, here it is 1 by a, and an is 1 by n. Sequence a n is 1 by n. Therefore, from there, limit xn equals x, hence limit 1 by 1 plus na equals 0. Okay. Now, again, Draw another one. Limit 1 by 2 power n equals 0. Limit 1 by 2 power n equals 0 for all n falling n. Limit 1 by 2 power n equals 0 for all n fallen n. So for we have n less than 2 power n for all n fallen n. We know that n less than 2 power n for all n fallen n. Therefore 1 by 2 power n strictly less than 1 by n. Okay. Now consider that epsilon is positive. At epsilon positive, then again 1 by epsilon positive, then by Archimedean property there exists k falling n such that yes, 1 by epsilon strictly less than k, means 1 by k strictly less than epsilon. Then consider modulus of 1 by 2 power n minus 0 equals 1 by 2 power n, but 1 by 2 power n less than 1 by n, then which is less than 1 by k, because for all n greater than or equals k. So it is less than epsilon, hence we have limit 1 by 2 power n equals 0. Immediate. Again, if 0 less than b less than 1, if 0 less than b less than 1, then limit b power n equals 0. Now that limit b power n equals 0. If b lies in between 0 and 1, then limit b power n equals 0. How? 0 less than b less than 1. B lies in between 0 and 1. So put b equals 1 by 1 plus a, with a is positive. Since b lies in between 0 and 1, we can construct this b as, or choose b as, b equals 1 by 1 plus a, where a should be positive. Therefore, what about b power n? B power n equals 1 by 1 plus a all raised to a. 1 by 1 plus a all raised to a. That means, but 1 by 1 plus a, or 1 by 1 plus a all raised to a. But by Bernoulli's inequality, 1 plus a all power n greater than or equals 1 plus n. 1 plus a all power n greater than or equals 1 plus n, 1 plus a all power n greater than or equals 1 plus n for all n fallen n. This is by Bernoulli inequality. So that means 1 by 1 plus a all power n less than or equals 1 by 1 plus n. Okay. For all n fallen n. Now consider. Now modulus of b power n, we have to show that limit b power n is 0. Consider modulus of b power n minus 0. B power n minus 0 equals modulus of b power n. Modulus of b power n equals modulus of 1 by 1 plus a all power n. So that is less than or equals 1 by 1 plus n. But 1 by 1 plus n, 1 by 1 plus n in previous problem, you see that it is less than or equals 1 by n. It is equals 1 by n into 1 by a. Then choose c equals 1 by a and sequence an equals 1 by n. Then by using that theorem, we have limit b power n equals 0. Agree? X equals x and be a sequence of reals, sequence a and be a sequence of positive reals, such that limit an equals 0, then for all m fallen n, there exists epsilon positive, such that modulus of xn minus x less than or equals c into an for all n greater than or equals m. According to that argument, here sequence n is 1 by n, c is 1 by a, sequence of positive, sequence a and b have sequence of positive reals, instead of m it is c, so modulus of xn minus x less than or equals c into an. So according to that theorem, limit b power n equals 0. When b lies in between 0 and 1, then limit b power n should be 0. Agree? Now, we'll try to prove if c greater than or if c equals 1, what about limit c power 1 by n? If c equals 1, limit c power 1 by n equals 1. Okay, that's immediate. If c greater than 1, then again you have to show that limit c power 1 by n equals 1. Also, if c less than 1, also to prove limit c power 1 by n equals 1. So try to prove these two arguments. If c greater than 1, limit c power 1 by n equals 1, and if c less than 1, limit c power 1 by n is also